Hello, and welcome in my brief introduction of the continuous BDPI paper. So it's a long talk, but should be a little bit more than 20 minutes only. So the main idea of continuous BDPI is that BDPI is an existing algorithm for reinforcement learning, but that is limited to discrete actions. I will explain all that later. And the idea is to make it compatible with continuous actions that are different kinds of actions. In a way that preserves as many good properties as possible of BDPI. So first, we are in the reinforcement learning setting. There is not much to say here because it's a workshop on also reinforcement learning, so most people watching should be familiar with it. But what I will focus on is the arrows here between the agent that learns and the environment itself, and mainly the actions. So most current reinforcement learning algorithms, they are compatible with rewards that are floating point values, states that can be discrete states, so just integers, or vectors of floating point values. And then there are two families of algorithms depending on whether the action is an integer, so there is a finite number of actions, they are numbered between 0 and n-1, or the action is a set of floating point values, so the same as continuous states. So continuous actions, so actions that are set of floating point values, they are useful especially in robotic tasks, in basically any control task that requires a precise control signal that needs to be possibly a multi-dimensional floating point value. In the case of this example, every joint here has a motor that can, at every time step, has its torque set, and so it requires the emission of several floating point values every time step for controlling that robot. So BDPI is a very sample efficient model-free reinforcement learning algorithm for discrete actions, and in this paper I will present how to make BDPI work with continuous actions. So first I have a very brief introduction of BDPI, that stands for Bootstrapped Dual Policy Iteration. It doesn't really matter here, it's the paper that's cited in the paper I'm presenting. It's an algorithm that has several components. Here I'm only giving a simplified view of the algorithm. So it is what we call actor critic. So that means that it learns both a critic, so Q values, that will learn how promising it is to execute one particular action in one particular state, and an actor that will directly learn to map a state in the action that has to be executed. So in the discrete BDPI paper, it's shown that BDPI outperforms many actor-critic, actor-only and critic-only algorithms. And so, well, it is promising. I will show that on the next slide. But now, when we want to make BDPI compatible with continuous actions, we have a few mathematical problems. So first, the critics in BDPI are what we call off-policy critics. So that means that pi here for the actor does not appear in the update equation of the critic. The critic learns how promising it is to execute an action in a state in the best possible case. It's not assuming that a given policy is being followed. And mathematically in the equation, that means that we have a maximum over actions that appears here. No problem if the action is an integer or there's a finite set of actions. We can just iterate over them, and then for each of them compute a Q value here and then take the maximum over those values. But if the action set of the agent is continuous, so if actions are vectors of floating point values, computing this maximum becomes untractable. So it requires advanced algorithms to do that. And the same problem happens in the actor update, that basically the actor is trained so that it executes the action that the critics think are the most optimal. And so instead of a maximum, we have an arc maximum, but it's basically the same operation, except that this returns the value and this returns the action that had the largest value. And so we again have the problem that we cannot enumerate the actions. So why bothering with that is that BDPI in the discrete BDPI paper outperforms a variety of other algorithms. So this particular graph is not that important to look at in detail. It's learning curves, so episodes on the x-axis and returns on the y-axis. BDPI, discrete BDPI, is the black line, and we see that it is always on top. It rises higher than the other curves. Here, for instance, it is always the first curve to rise, so it's a dominating algorithm, it's always better. And the other algorithms, the actor, PPO, are well known. This is bootstrap DQN, and then those are variants of BDPI that show that both its actor and its critic are necessary, and this is BDPI that outperforms every other algorithm. And it was done in a large variety of environments, and so they had different properties, high dimensionality, pixels, so high stochasticity, difficult to explore. And so now what we want to do is that discrete BDPI has some properties. For instance, it's, to my knowledge, the only reinforcement learning algorithm that is actor critic with off-policy critics. So not off-policy actor critic, off-policy critics in the actor critic algorithm. It's explained in the paper that it's different. So we want to keep that off-policiness of the critics, but with continuous actions. So we need to find a solution for the max problem. And we want to keep the stochastic actor, so the actor of BDPI, and we need then to solve the arcmax problem. So now I will present what is being proposed. So first, when the action is a floating point value, we need to pay attention to how we encode Q values. If the action were discrete, having a neural network that encodes Q values is easy because it just takes a state as input and then it has one output per action. But here, because there is an infinite amount of actions, we need a network that its general structure takes a state and an action and then outputs a single floating point value that is the Q value of that action in that state. So here I forgot an arrow between state and this. So it's what we call a dueling network architecture. So that means that it has two separate, it's not really heads, but I would say feet in that direction. One that only observes the state and predicts the value of the state, and then one that observes the action and the state, so the arrow that I forgot, and that produces an advantage value of that action in that state. So it's not mandatory to have that two-legged version of the neural network, but having a separate value and advantage prediction increases stability, because when we have continuous actions, it's extremely even more difficult than with discrete actions to have valid Q values, so that don't blow up or go too low over time. And then we have the fact that the value of a state minus the advantage plus the opposite advantage gives the Q value, so we can just have a minus operation here. So that's just the neural network structure that is used by the critics. It's relatively normal. It doesn't say how they are trained. So now when we want to move on how to train the critic, I first need to very briefly introduce what is a variational autoencoder. And so basically a variational autoencoder is a neural network that is able to learn a distribution. So in this case, the variational autoencoder has as input a state and an action and outputs an action. It's the same action. It's an autoencoder. It tries to recover the action. What will happen, but I invite you to read literature on the variational autoencoders, is that by training the whole network to output the same action as this action here, inside the network, there is a sampling operation from a Gaussian that will basically allow the network to learn how to map samples here of nodes, that is called Z. So a noise vector, just a random value, plus a state to an action in that state that follows the same distribution as the distribution of actions in that state that have been seen during training. So basically, this is a network that can learn what are usually the actions that are executed in that state. And that's useful. So it's useful because it allows to solve the max problem that we had for the critics. So in this case, instead of having a maximum over every possible action, which is impossible, it's a maximum over a finite, like 50 actions that are sampled from that variational autoencoder in the next state. And so that's nice because now we get actions that are somewhat credible, so actions that are often generated, and it's a finite set of actions for which we can compute Q values. So the idea, yes, I forgot to add the citation here, it's cited in the paper. So the idea of using that variational autoencoder for Q values comes from batch constraint Q-learning. So it's a different setting of reinforcement learning, but it uses also an off-policy critic, no actor, and a variational autoencoder to implement that maximum operation. So that's one side of continuous BDPI. We need the addition of that variational autoencoder to be able to train the critics. So now we can focus on the actor. And the question is, can the actor be also a variational autoencoder? In that way, we could have the actor that observes once trained a state plus a noise vector, so randomly generated, uniform, and so on, and outputs an action. So that would be an actor, that would be nice, it is stochastic, and so on. But we have a problem. Variational autoencoder, when they are not yet trained, so when the agent is young, for instance, have a tendency of mapping any noise vector and also any state to always the same action. This is shown, if we can say that it's shown here. This is a variational autoencoder that is supposed to predict images, and this is what it outputs when it has not yet been trained. So just building the network in PyTorch and then just giving it noise vectors, and those are the images that come out. We see that they're all the same. And so that means in reinforcement learning that we cannot use that as an actor, because that would mean that the agent, when not yet trained, would not explore at all. Whatever happens, the agent would always execute the same action. So the solution that we propose in the paper is to replace that variational autoencoder with what we call a discriminator, combined with something that is called rejection sampling. So the idea is that we have a much simpler neural network here that observes a state and an action, and basically it predicts how likely it should be to execute that action in that state. So here it's a floating point value between 0 and 1. And so how we sample that actor is with rejection sampling. So that means that we sample actions uniformly in the space of possible actions accepted by the environment. In this example, the action is a single float from -1 to +1. And then for each action, we pass it through the neural network, get a probability of accepting it. And so if there is a random number here uniformly sampled between 0 and 1 that is smaller than the probability of accepting the action, we accept it. So we stop the iteration and we execute A in the environment. And so how can this work? Is that when untrained, that network will basically map any state action pair to the same probability here, which means that it has no preference. So because we sample those actions uniformly, then maybe the fifth will always be accepted or something like this. And so we see that in the early stages of learning, we have full uniform exploration in the environment. This is what we want. And then as the actor is trained, we'll see in the next slide how it is trained, we see that it starts having a preference. It accepts actions close to 1 and then close to -1 after some time with a higher probability, and that changes the distribution of actions being learned. So how do we train that? So we need to have an arg maximum here. So in this case, it's a work in progress paper, I would say. We don't have a nice solution for the argmax problem. So the idea is to just sample a large amount of actions uniformly at random in the space of possible actions, query the critic for all their Q values, take the action that has the maximum Q value, and train the actor in that direction. So training the actor in the direction of that action is made by telling the actor, so the discriminator network, that the probability of accepting the action that is here, the argmax, should increase from a small value when being trained. And then to prevent that actor from just predicting 1 for every state and action, we also need to tell it that for some other counter example, so we sample a second action uniformly at random in the space of actions, and we tell that actor that the probability of accepting that action should decrease. And so now there is a nice balance that takes place. So the probability of good actions increases and the probability of bad actions decreases. And that's it. Well, more details in the paper, but the general intuition behind continuous BDPI is given. And so for experiments, because it's a work in progress paper, so basically the algorithm is somewhat done, but the experiments are quite preliminary because it's an algorithm that takes from this January. So it's only one environment, and it's bipedal walker, so available in the gym, and it's basically a sort of 2D robot that has to walk. It observes a few LiDAR readings of the shape of the ground, and it has an action that has 4 dimensions. It's basically the torque of the 2 hip joints and then the 2 knee joints of that robot. And basically what we see is that if we compare continuous BDPI, so same BDPI, with the soft actor critic that is currently the state of the art, in that environment, we see that continuous BDPI is more sample efficient. So it reaches about the same height here, so a little bit of noise, and it goes higher earlier. And here it's even more dramatic. So it's like several times faster before the robot like completely collapses on the floor. And we see that the advantage remains over time. So it's not as dramatic as the results of discrete BDPI, but it's also like an algorithm that is still being developed. It shows that the idea of a discrete action BDPI, so the off-policy critics and its particular actor, translate to continuous action settings. And so that's promising for future work when we need to address that argmax problem and do something a little bit smarter than sampling a uniform function, and hoping to achieve sample efficiencies that are even better than that. So that was a quick introduction of continuous BDPI. BDPI, sample efficient, model free for continuous action spaces in reinforcement learning. Yeah, so feel free to ask questions in the chat. We have like 1 or 2 hours during which we can ask questions. And the paper should also help with the nitty-gritty details on how it has been implemented and things like that. So thank you for your attention and for having watched the video until the end. And I welcome questions, feedback, comments, and so on.